Hi, this is Dr. C. Lakshmipati, Associate Professor of Physics, HNS Department, SRIT Engineering College, Anantapur. So today we are discussing about Unit 3, Dielectric and Magnetic Materials. So what are the dielectric materials and what are the magnetic materials? So here, first of all, we have magnetic materials, magnetic dipole moment or magnetic moment. So the product of the pole strength to the length of the magnet is known as magnetic dipole moment. So here magnetic induction, it is defined as the number of lines passing per unit area is known as magnetic induction or magnetic flux density. It is indicated by B. Next we have the definition, basic definitions of magnetic flux. Magnetic flux means the product of the magnetic induction and the area of the material is known as magnetic flux density. Next definition we have the magnetic induction or magnetic flux density. Already we discussed about the number of lines passing through the unit area known as magnetic induction. Next, magnetization or magnetic field intensity. The force experienced by unit north pole placed at a point is known as magnetic field intensity. Next, we have the magnetic susceptibility. The ratio of the magnetization to the magnetic field intensity is called magnetic susceptibility. Next, magnetization. The magnetic moment per unit volume is known as magnetization. Next, we have the relation between the next permeability. Permeability means the ratio of the the product of the relative permeability to the relative permeability of the free space is called permeability. The value is 4 pi into 10 power minus 7. Next, we have the relation between the BHM is, we know that B equal to mu naught into H plus M. The relation between the mu r and psi is mu r equal to 1 plus psi. So next we have the origin of magnetic moment. So the orbital motion of an electron, orbital magnetic moment is describes the magnetic moment orbital equal to minus E by 2m into Lh by 2 pi, that equal to minus mu b I. Here mu b L. Here mu b equal to E L H by 4 pi m. This value is equal to, this is known as Bohr magneton. That value is equal to the 9.27 into 10 power minus 27 ampere per meter square. Next we have the very important topics we have. What is that? Hmm. Classifications of magnetic fields. So there are some type of magnetic fields are diamagnetic materials, paramagnetic materials, ferromagnetic materials, anti-ferromagnetic materials, ferrimagnetic materials. So here magnetic materials we have five types which is already discussed: diamagnetic material, paramagnetic material, ferromagnetic material, antiferromagnetic magnetic material, ferrimagnetic material. Next, first one we have, what is that? Diamagnetic material. So which is diamagnetic character is a substance that have only non-magnetic atoms. So it is repelled by the magnetic materials is known as diamagnetic materials. So here the electron moving around the nucleus result in magnetic moment. Due to the different orientation of various orbit of an electron, net magnetic moment is zero. So in this one, the magnetism is also exist in substance with magnetic atoms, but very weak and compulsory masked by the contribution of magnetic atoms. So then we have the magnetic materials classifications we shown in paramagnetic material. It is slightly attracted by the magnetic materials. Next we have the ferromagnetic materials. It is will be attracted by the strongly attracted by the magnetic materials. Next, antiferromagnetic material. It is also related to ferromagnetic material. Next, we have the ferrimagnetic material. Antiferromagnetic material and ferrimagnetic material are related to the magnetic materials. Okay, so special case of antiferromagnetism. Magnetic a net magnetization of magnetic sublattices is not zero since antiparallel moments are of different magnitudes. Hence, ferromagnetic materials possess a net magnetic moment. This moment disappears above a Curie temperature analogous to the Nile temperature. About CTC, thermal energy randomize the individual magnetic moments and the material becomes paramagnetic. So the magnetic domains becomes magnetic bubbles to act as memory elements. Okay. So here have the classifications of magnetic materials in tables. We shown that the paramagnetic magnetic properties. Permanent dipole moment is in the diamagnetic material is no. Paramagnetic material yes. Ferromagnetic material yes. Antiferromagnetic material yes. And ferromagnetic material also yes. Next property, origin of magnetic moment. So orbital magnetic moment here, orbital plus spin magnetic moment here, spin magnetic moment and spin magnetic moment and spin magnetic remaining materials. So spin alignment is shown in the figure. So diamagnetic material there is no response. Randomly oriented that results magnitude is equal to 0. Then parallel, next anti-parallel and anti-parallel in the remaining magnetic materials. Effect of magnet. So repulse the magnetic flux. Here attract the magnetic flux. Here strongly attracted by the magnetic flux. So here attract the magnetic flux. These here also attract the magnetic flux. So then the effect of temperature, it is independent in the diamagnetic material. In the para, chi equal to C by T. In the ferromagnetic material, chi equals C by T plus or minus Tc. Next, in the antiferromagnetic material, psi equal to T by T plus theta. In the ferromagnetic material, psi equal to C by T plus or minus theta. Then permeability less than 1. Here, less little greater than the unity, here very high in the antiferromagnetic material, little greater than the unity, and in the ferromagnetic material little greater than the unity. Next, susceptibility small and negative in the diamagnetic material. In the paramagnetic material small and positive. In the ferromagnetic material very large and high value and positive value. So in the antiferromagnetic material positive and small, in the ferromagnetic material positive and small. Examples in the diamagnetic material, example copper, silver, gold. In the paramagnetic material, lithium, tantalum, and magnesium. Next, in the ferromagnetic material, iron, cobalt, nickel, cadmium. Next, here salt of transitional metals. Here ferrites in the ferromagnetic materials. So these are the properties of classifications and properties of magnetic materials. Next, domain concept of ferromagnetic material. We proposed these concepts of domains in 1907. What is domains? A region in ferro or antiferromagnetic materials where all the magnetic moments are aligned in a same direction is called a domain. Ferromagnetic materials is divided up to into these small regions are called domains, each of which is at all times completely magnetized. So atoms with similar magnetic orientation like line up with neighboring atoms in groups called magnetic domains are shown in the figure. Next we have the hysteresis curve. So what is the hysteresis curve or hysteresis behavior? The meaning of hysteresis is lagging. That means hysteresis is characterized as a lagging of magnetic flux density behind the magnetic intensity is known as magnetic behavior, hysteresis behavior or hysteresis loop. So whenever the magnetic flux density is not zero and applied intensity is zero, then the remaining magnetic flux density is known as retentivity. Then whenever the retentivity, the magnetic field is zero, induction is zero, there is the magnetic field strength is not zero, then the magnetic field is known as coercive field. So then we get the one positive retentivity, one negative retentivity points, and one positive coercivity and one negative coercivity points. Finally, it will be passes in a particular shaped curve. Then the shape is known as BH curve. Next, it shows the loss of the energy in the magnetic materials. So here, according to hysteresis sleep, there are two types of magnetic materials are there, which is soft magnetic material and hard magnetic materials. Hard magnetic materials are those which are characterized by large hysteresis loop because which they are retain a considerable amount of their magnetic energy after the external magnetic field is switched off. That means which magnetic material hardly magnetized or hardly demagnetized, then the material is known as hard magnetic materials. So properties: high retentivity magnetization, high coercivity, high saturation flux density, low initial permeability. Next, high hysteresis energy loss, high permeability. The eddy current loss is low for ceramic type and large for metallic type. An example: iron, nickel, aluminum alloys with a certain amount of cobalt called okay alnico alloys. Next, applications of hard magnetic material. For a produce of permanent magnetic material, it is used in magnetic detectors and microphones, flux meters, voltage regulators, damping devices, and magnetic separators. Next, soft magnetic material. Which material easily it will be magnetized or demagnetized. Then the magnetic material is known as soft magnetic material. Then the area of the hysteresis loop will be small. So properties: low retentivity magnetization, low coercivity, low hysteresis energy loss, low eddy current loss, and high permeability, high susceptibility. Okay, examples: param, perma alloys, like alloys of iron and nickel. That is, applications of that soft magnetic materials are mainly used in electromagnetic machinery and transformer cores. They are also used in switching circuit, microwave isolators, and matrix storage and computers. Applications of magnetic materials. Okay, power and electrical applications, and medical and biological applications, and industrial and consumer applications are there. Next, we have the dielectric materials. So, what are the dielectric materials? Dielectric materials is behave like a insulator. Okay, so shown in the figure. Next, introduction. Dielectrics are the materials having electrical dipole moment permanently. Which material having the permanent dipole moment? Then it is called dielectric material. Dipole. A dipole is a entity in which equal positive and negative charges are separated by a small distance is known as dipole. Next, dipole moment. The product of the charge connected to the separated distance is known as dipole moment. Next, it is shown in the figure. Di- Dielectric polarization. So, dielectric polarization occurs when a dipole moment is formed in a insulating material because of an externally applied electric field. Okay, so when a current interacts with a dielectric material, will respond with a shift in charge distribution with an positive charge aligning with the electric field and the negative charges aligned against it. Okay, dielectric polarizability. Dielectric polarizability means the ability of the dielectric material to get polarized. It introduced dipole moment is proportional to the intensity of the electric field. Then we get the alpha equal to mu by E. Next, so the relation between the dielectric parameters relation, that is D equal to epsilon naught E plus P. Next, the relation between the polarization and dielectric constant is epsilon r minus 1 into epsilon naught E equal to P. Next, we have the dielectric susceptibility and dielectric constant relation, chi equal to epsilon r minus 1. Dielectric constant equal to the ratio between the permittivity of a material to the permittivity of a free space is called dielectric constant. Epsilon r equal to epsilon by epsilon naught. Next, displacement of vector t equal to epsilon naught t plus p. Relation between the electron vectors, that is the d equal to epsilon naught t plus p. Next, there are types of polarizations, are three types of polarizations are there. One is electronic polarization, ionic polarization, orientation polarization, and space charge polarization. Four polarizations are there. So first one, electronic polarization. So what is the electronic polarization? When an electric field applied on a dielectric material, then all the positive charges nucleus displaced in a direction of the field. All the negative charges electron cloud be atom move in opposite direction to the applied field. Then it is known as, then forms the dipole moment. Then the process is known as electronic polarization. Mu E equal to alpha E, then alpha E equal to 4 pi epsilon naught R cube. Next, ionic polarization. Ionic polarization means ionic polarization occurs due to the displacement of ions and cations in opposite direction and occurs in the ionic material when placed external electric field. When the atoms or molecules, and it is mainly due to the relative displacement of the atoms components of the molecules in the presence of electric field. Then alpha ionic equal to mu ionic by E, that equal to E square by W naught square into 1 by E small m plus 1 by capital M. Next, orientation polarization. It is also called dipolar or molecular polarization. All the molecules dipoles are oriented randomly when there is no electric field. In the presence of electric field, these dipoles oriented themselves in a direction of field. As a result, net dipole moment becomes numerous, is known as orientational polarization. Alpha equal to mu naught square by 3kt. Total polarization equal to alpha electron, next plus alpha ionic plus alpha orientation. Internal field or local field. So the total electric field acting inside the atom at a point in the dielectric material is known as internal field or local field or Lorentz internal field. So here we have what is that total field E equal to E1 plus E2 plus E3 plus E4. Then we get the E1. E1 equal to E plus P by epsilon naught. E2 equal to minus P by epsilon naught. Next total electric field we get. So here E3 field will be inside the circular is 0. Then the charges will be displaced symmetrically. Next, E4 you want to determine. So E4 value we can determine by using the diagram. That is, we know finally we get the E4 value, that is DE4 equal to manaku, we know that P by 2 epsilon naught cos square theta sin theta d theta. Then after integration we get the E4 value. E4 equal to P by 3 epsilon naught after solving. Next, finally, we get the internal field or Lorentz field Ei equal to E plus P by 3 epsilon naught. Next, Clausius-Morsky relation. It is the relation between the dielectric constant and polarizability is called the Clausius-Morsky relation. Then Clausius-Morsky relation, P equal to, we know that n alpha e by 3 epsilon naught equal to epsilon r minus 1 by epsilon r plus 2. Then we have the frequency dependence of polarization. So here we have the polarizability will be decreases with the frequency and it will be finally disappears with the different region, microwave region and ultraviolet region and infrared region. So in this topic we discuss about what is that magnetic materials, basic definitions, and we have the classifications of magnetic material, origin of magnetic field, domains, and hysteresis behavior, and soft and hard magnetic materials. And fine, next we have the dielectric materials. So dielectric material basic definitions, and we get what is the types of polarization, electronic polarization, orientation polarization, ionic polarization, and spatial polarization. Next, we get what is that discussed about Lorentz internal field or local field and gaseous moisture relation and frequency dependence of a dielectric is discussed. Dielectric displacement. That means the polarizability is depending on the frequency is discussed. Okay, thank you.